small test site having 1.2 lakhs data covering this piece of remote sensing data. And it generated, you can see that net radiation, soil heat flux, aerodynamic resistance for heat transfer, sensible heat flux, latent heat flux, and finally the actual evapotranspiration has been estimated using remote sensing based regional evapotranspiration through surface energy partitioning. The another component which I said that root zone soil moisture, we found it is difficult to, we tried several correlations between the remote sensing derived parameters like albedo, surface temperature and NDVI. We tried to establish the relationship, but it was not very good. Another derived parameter was the evaporative fraction, which has come from the RECEP. We tried and finally used for the purpose of estimation of the soil root zone soil moisture. The problem was that it was not giving very good correlation. So we employed the artificial neural network here for estimation of the root zone soil moisture. You can see it is derived, and this is the ET also, because this work was done on 16 February 2000 data of the Landsat TM, and you can see that it was taking too much time to calculate, and that's why we thought that whether the ANN can also be employed for cutting the time and efficiency. It should give the real time, because it was taking almost 36 hours of calculation times because of the several intermediate files, around 33 files it was creating of 1.2 lakhs data. So it was a huge data at that time when I started this work in 1997 around. And you can see that when we generated different RECEP based ETA, actual evapotranspiration, then artificial neural network based ETA and the regression based ETA, you can see here the histogram here, and you will find that the remote sensing based and artificial neural network is having the same frequency analysis and compared to the regression methods. And the same technique has been employed by extrapolating the remote sensing derived evaporative fraction and correlating it with the root zone soil moisture. This is the image that has been created, and this has been subsequently employed for a larger entire canal command data. This is the entire canal command data which I have shown you, and finally we worked out for each date the actual evapotranspiration and the crop yield for the for wheat crop, which was major crop in that irrigated command area. We worked out for all the statistical analysis we did for all the branch canal as well as the distributaries for evaporative fraction, actual evapotranspiration, and DVI and yield. You can see when it is like the yield is reducing when you are moving away from the head of the distributary, and as you move towards the down tail end side, the water availability is less, and also the yield was less. Similarly, we estimated, based on this remote sensing analysis, we estimated the water productivity, and there was some technique in between which we employed, but finally you can see that the evaporative fraction at evaporative fraction as well as yield and the water productivity in kg per meter cube for branch canal level as well as the distributary level, this has been worked out. So this is one of the application that one can do. Then finally the question comes, what is the decision making? Ultimately the aim of any research is the decision making, and we developed this software called as Canal India, and where we employed the water supply system from head to tail, and how the crop water demand which is coming was generated for entire all distributaries as well as for entire canal command, and the supply and demand that were matching, or it should closely match. That was the target of the entire exercise. So this was used for the purpose of decision making by the policymakers. The second case study which was done for the assessment of waterlogged and salt-affected crops in canal irrigated command, which is a major problem in Punjab and Haryana. And what we did, this was again the Landsat 7 ETM input data, which we use the raw data and the GIS based image, and then superimposed image on the raw data. This was the basic concept, which was the albedo, surface albedo, which was derived from remote sensing and the NDVI. We found a pattern in the salt affected and waterlogged area, and for that purpose, first we suppressed all this non-cropped area, and only the cropped area having this side, all salt affected area, because wherever there is a salt presence is there, reflectance increases. Whereas if the water logging is there, reflectance is, it decreases. So this waterlogged area, and we have bifurcated all this slightly affected because of NDVI. Higher NDVI was taken as a normal crop and rest has been segregated. This algorithm was developed for the purpose of estimation of these segments, and a software has been developed, and this was employed for generating the input for, of course, for giving the input, and then the intermediate, and finally the output. And these are the output which has been intermediate output, the surface albedo, NDVI, and yield image. And based on this, we use this classified image, which was based on the analysis, and a number has been given like 0 to 7, where the 7 was the normal crop, and accordingly we have analyzed this entire study area, which you can see here classified, and it is the histogram given here, and the percentage area which is affected under different salinity or the water logging has been worked out based on this. The advantage of this this was also validated using the ground truthing. The advantage of this kind of study is that you can work out that because of the salinity or water logging, how much losses that is happening, and it was estimated that in that 80,000 hectares area of the Balod branch canal command, 18% potential it is lost because of the water logging and salinity. There are myths that the remote sensing and GIS and this kind of techniques are very costly. We worked out, and at 2006 prices, it came around 0.75 rupees per hectare for this kind of analysis. So roughly almost 1 rupee per hectare. This was the cost, which is very, very little cost for the purpose of analysis. The third case study was relating to the spatial decision support system for improving water productivity in irrigated saline environment. Here, because the farmers, they take certain decisions. The very idea was that you generate all the information, whether it is the canal network related information, design discharge, soil and groundwater salinity, cropping pattern, all these information should be the base for the spatial decision support management system. And the farmers' practice, which was monitored, in our case, we monitored some 216 farmers for 2 years. All the water management and crop related information were collected and systematically analyzed for the purpose of predicting the farmers' practices through artificial neural network. And regression models were also used, but they were not that good, and I will come to that. And another was the physical model like SWAP and CropWatt, which was used for the purpose of the salinity related the estimation. And the farmers' practices were evaluated plus scientific decisions, whether they can improve upon the farmers' practices has been compared to know whether the decision of the farmers are good or we can improve upon to their decisions. For that purpose, we generated the spatial information for the entire Punjab and Haryana, the different districts. This is the cropping pattern, the water quality, the tuber density, and also the water table, whether it is rising or falling. Software was developed where you can touch the India map, then you will reach to Punjab or Haryana, and then you will finally come to your own field. And if you touch your plot, you will get all the information relating to the field area, the crops, the groundwater salinity, EC, all that information you will get. And this information becomes the input for the SWAP model for the purpose of estimation. But as I said that in one component, whether the farmers' practices we can predict, we employed this artificial neural network, and this is well known now. There is no need for describing it, but these are the data, the different two miners which we have selected, and different miners we selected 216 farmers, and these stratified data has been utilized for the purpose of prediction. This is the architecture that was employed for the ANN, and the options that we use for the ANN prediction, like the water quality and all that information, the input variables, and this was employed for seeing whether the number of input data, how many are adequate for the purpose of training the ANN, and what you can see that the ANN performance with different techniques like back propagation, Levenberg, Mercadect, and the radial basis function. The best we found that the RBF was the better in comparison to all these two methods, and we employed later on that method. And the size of the input data, that also we worked out that what should be the optimal data. Accordingly, we found that if we have this kind of number of data, somewhere the 108 and 54 data for validation purpose, the results were much better. So we've taken that much data, and also the variables which can ultimately lead to the prediction. So the different variables we employed, and we found that if we use 5 variables, we will get the better information. So we employed this combination for the purpose. This is a SWAP model calibration, and validation also has been done just to show. And this is for the purpose of decision making, where the relative yield using the farmer's decision making or the scientific decision making, if the canal water, because we have developed several such nomograph for water availability at head, middle, tail. A farmer may get 10 centimeter water of canal and 5 centimeter of canal, or even no water, but he uses the saline groundwater of different quality and magnitude. So how much loss will happen? But finally, what decisions against the farmer's decision, we found that the scientific decisions, if we can go for frequent application of the water, can lead for the similar conditions, can improve the yield of the farmers in that saline irrigated area. So this is how the different component of ANN has been employed for the purpose of decision making. That is what I wanted to share. Beside this, also some of the work which has been done by the students for prediction of the district yield forecasting, and also the combinations for the neurophysi or the ANN genetic algorithm ANN method. So these combinations have also been used for some other purposes, and but at this moment I will say that this is what we have done in the past, and in the future maybe the line is open for such combination which can be employed for the even commodity marketing, comparing the what is the global scenario, how the different country is having the say bad weather, and then the production is going to reduce, and that can be estimated well before the hand, and the farmer's optimal area under different crops can be predicted or maybe suggested, so that the market glut or the surplus, or because of the shortage, that kind of situation should not be created, considering the global scenario. Thank you very much.
Thank you. We can have the questions at the end.
Thank you, sir.
So the next presentation by Dr. S.K. Som.
The Honorable Chairman of the session, Dr. A.K. Singh sir, the rapporteur, Dr. Chakravarti, the Director NAM, Dr. C.H. Srinivasa Garu, all the respected directors of the institute and the respected participants of this workshop. I share with you the human resource development angle, which is the main responsibility of NAM, and I share some of the activities which has been done by NAM during this period. First of all, during January, we included one module in one of the training program, and we saw the response of the people, that how do they respond about these kind of things. Then during March and April, we conducted one questionnaire survey with around 200 trainees at NAM, and the two groups. One is that newly recruited, just newly recruited, the scientist and the assistant professor of the universities. They are not exposed to the system till now, and the few who has the service around 7-8 years in the system, either in ICAR or in the agriculture university. Then during May period, we did some kind of literature survey of the existing situation and some of the databases, those kind of things we did. And there was a visit of a group of 10 people where I was also there, and the director NAM was also there. And then we had visit in Australia and New Zealand and Singapore, and my main job was to look the things towards from this perspective. We shared our responsibilities in different aspects. Then in June we conducted one national dialogue where around 45 senior people, principal scientists, they participated this one-day workshop, and some kind of the recommendations has come. Then there was a responsibility to write a policy brief so that which can become the input for this workshop, which was released yesterday. If you look to the trends, especially for the young people, we did this analysis from Web of Science, which is the top database. So fortunately we have at NAM. If you look to here, there is a great change between 2017 and 18. The data is just 3-4 months data is there. But if you look to the 16 and 17, there is a great change in the publications. The number of publications has just jumped during this. So this is a learning that this is the area we should publish. And not only the publication, if you look to the citations, on an average, more than 1,500 times each article has been cited. So this is the area where we should come from the HRD perspective. We should come into this area as far as the publication is concerned. Our people has to be active in this particular area. Now look to the some of the survey results which I can share with you. What is the level of the awareness of the let us say artificial intelligence? So 70%, more than 70% are aware. But when we say that domain knowledge in agriculture, it is only 34%. So they know that artificial intelligence, but how do we apply in agriculture perspective? That is the one area where work has to be done. The similar kind of result come for the IoT also. The same thing. Here it is even 28%, which says that yes, they know about the domain. Now, looking to that, is there any difference between the newly recruited and those who have the service of 7-8 years? So that also we gauged, and here we can see that the middle level people have a little more knowledge as far as the AI this knowledge is concerned, and similarly for the IoT also. This is the middle level, this is the new level. So there is not much difference, only in this AI little because of the experience the middle level has more knowledge. Now look to the domain knowledge. The general knowledge is fine, but when we look to the domain knowledge, so our middle people are very less. They only 10% has some kind of knowledge that what can be the domain knowledge, and here also the same way. But overall, if you see, it is only around 30%. So around 30% people, they have some kind of domain knowledge. So that's why the new people and the middle people, they have to be little more innovative as far as the literature and all those things are concerned. When we look to that, what do they know actually? So when we classify their complete thing, so we can say that this is the distribution. In their opinion, 37% are for the prediction services, that this AI and IoT which can be used, and followed by prescriptive services, and then advisory services and diagnostic services. So these were the areas which our people think that where this AI and IoT application can be there. We did some kind of search that what are the main applications going on in the market and where the people are using it. So some of these are the only software. These are the applications, and no devices required, and few, for example, TensorFlow. TensorFlow is the most wonderful, freely available, open access, and the experiment have been done for potato in several countries, and it is highly successful. And image recognition, and it is going on very nicely. Plantix. To the selected applications, we are asking officially the data that how many people are using these applications. Plantix, 400,000 people in India are using Plantix, which were the registered user for this. And then several others are also there. This ripe sense we have seen in New Zealand. Kiwi, what do they like? They like a little sour kind of kiwi. So they don't like a sweet kind of kiwi. And this particular application is being used for kiwi that went to harvest. And I will suggest, especially to our younger generation, that at least TensorFlow, they let them start using. It is a ready-made application, and only thing that you have to take image and you have to put all those kind of things. When it comes to image analysis, in our June workshop, Dr. Nachiketa, he is here. In his presentation, he said that artificial intelligence is more intelligent than the natural intelligence as far as the face recognition is concerned. There is a study of California University where they say that a person is able to understand only 7. If it is a similar kind of faces, he can differentiate only between 7. So, for example, if you have children more than 7 and the similar kind of face, you cannot recognize by name. And this is a study by California. So, he is true that artificial intelligence is more intelligent than natural intelligence. We had a lecture of Dr. Kanuja, a director, retired director of CMAP, and he's a wonderful man, and he's a governing body member of NAM. A wonderful lecture. Sir, you were not there on that day. So, what is said that you are seeing me, but if I cover my face, you cannot see me, who I am. You cannot identify. You are identifying me only with my face. But the AI can identify through your whatever DNA or this and that kind of thing. So, AI is more intelligent than the natural intelligence as far as the image processing is concerned. So, TensorFlow can be used. Plantix is also freely available, but problem with the Plantix is that through Plantix, this Germany-based company is getting the old data of the Indian agriculture, complete data of Indian agriculture. So that is the only thing which is there with the Plantix. Similarly, some of the platforms which are the device-based one. So these are some of the important platforms which are being used in our country and also elsewhere in other countries. And we can see that if some of them we can use. Now, some of the recommendations which have come out of this workshop which we conducted during 1 to June. In this, we can see that so many for the crop sciences, but the main concern was data, the accessibility of the data, the validation, the quality of data, and all those kind of things. So, most of the recommendations which have come for the data in crop sciences, and in NRM. The main thing was that the creation of the databases. That was the main concern which has come one of the recommendations for the NRM. Of course, so many other things are also there in NRM. And similarly, for the fisheries, the main thing has come the traceability of the product. That was the main recommendations. And some of the recommendations, the integration, how to integrate. And in many time of the cases, the integration with CDAC, with the IITs, and collaboration with the private business enterprises. So that has come the one of the main recommendation. And also national level, a nodal point should be created. That was also one recommendation, that if some kind of nodal point can be created in ICAR. For the strategies, the main recommendation came that training to young and middle level scientists in AI and IoT in identified institutions abroad, which can be done. And then investment in projects and infrastructure. For example, our national fund and the other funds, if they can give some kind of boost, and the kind of hand-holding and support is required for private businesses in terms of capacity building and domain consultancy. So some kind of starts up and those kind of things. When we were in Australia, this university, Sydney University, so they have developed so many AI and IoT based devices, and they are in different phases. Some where they have given license, some which are in demonstration phase, and some which are in prototype phase. And different kind of devices are there, and including some of the devices which are for the small farmers also. In another university, the Western Sydney University, which is a wonderful infrastructure for the precision agriculture and climate studies, and they are also linking with the AI. So, if these two universities can be part of under either national higher education project or something, so that our students they go there or the scientists they go there under collaborative program. We looking to the public-private relationship. NAM has started one innovative initiative. We have empaneled the IT firms, and the empanelment is a different kind of the MOU which we have with the industries. They work with us. They develop the software. We facilitate whatever we can do from the NAM or from the ICAR, and whatever software is there, it will be free for that particular institute. And whatever the software is sold, we get 8% of royalty. So we are not giving anything to the company. We are just facilitating. Whatever they develop, it will be free for us whole life. And wherever they sell, 8% we get the 8% royalty. So this kind of empanelment we have done. So NARM can facilitate if some kind of thing is there. Already the companies are in place, and they are there. So thank you very much for giving me this opportunity.
Esteemed chairman, rapporteur, and directors, all the my fellow participants, and former director IRI and project director WTC Dr. Kaur is also present here. Welcome, madam. So before clicking on the mouse, I express my heartfelt thanks from the core of my heart to the organizers for giving me an opportunity to speak on this topic. So I will be just highlighting in very brief in my own words what is AI in a couple of slides. Then I will be presenting that what work myself and my group have done at WTC IRI on artificial intelligence. I will not be linking with GIS and remote sensing, only the AI work I will be presenting. So before starting that, we know that intelligence acquired from the natural, our intelligence is natural. So somebody is acquiring our intelligence is artificial. So how we'll be using our intelligence to run a computer and a machine? And the basic premise is that the better information acquired from a machine will lead to a better decision making. And the $1 million question goes, can a machine think exactly like human? So if you look into the artificial intelligence work in 1925, the work started in UK, but the word was coined by Professor John McCarthy of Carnegie Mellon University of Pittsburgh in Pennsylvania, USA in 1956. After that, the work was slowly progressing, and the goal is to create an expert system or the heuristics, the rule of thumb, how we can use all the heuristics and rule of thumb to develop the expert system and to implement human intelligent machines. So there are two things. One is a tangible resource and intangible resource, which we can feel, perceive, and touch. I am holding this as a tangible resource, and intangible. The softwares are intangible. But whatever work at WTC we have done, that is intangible. That is a software based. But if we can put that in a microcontroller, in a robotics, other things, that will be more tangible. You can feel that. So if you look into how the decision or the knowledge, the intelligence is intangible. We cannot see the intelligence of a person. We can touch a person. So there are basically 5 categories of intelligence. Linguistic, a person may be very good in the oratory skills. He should be an eloquent orator. So their capability, and then reasoning capability, then learning capability, perception capability, and decision making capability. So all these things need to be included. And if you look into artificial intelligence, it's not a single branch. It is a combination of so many branches. And there are different type of problems are there. The problems are very easy to solve, very difficult to solve, and very, very difficult to solve. So if you look into the application of ANN and the artificial intelligence, the difficult are in engineering, then financial analysis, the medical and scientific analysis. So here recently in the work of maybe 2-3 days back, they compared the different these engines that are in the microphones like your Siri in iPhone and Google Assistant, and what is the IQ level? That is also AI. So in my Apple system, if you ask a question to Siri, then what is the temperature now? Immediately the result, the answer will come. So that type of interaction, the voice recognition, the tool, and then coming to the background database, and then giving the output, also being very popular nowadays. So why not in agriculture we can develop such a tool so that the stakeholder, if you ask that how much fertilizer I have to apply, what type of irrigation scheduling I'll take, that will be giving the answer. So this is the time where we can think about this. Now, there is a perception among the academicians that only ANN is an artificial intelligence tool. But beyond that, because ANN, what is ANN? It is a cognitive response of the human brain. Because our brain consists of so many cells, neurons, axons. If an ant will bite us, immediately our other hand will go there and feel that pain. So it is a very complicated system, sir. It is a very conspicuous system. So this system of synapse, axons, and in the neuron is being converted to an artificial neural network, having a initial layer, input layer, hidden layer, and output layer. It is more synonymous to our brain. And besides that, there are certain neural artificial intelligence tools. They are called simulated annealing. It is not our branch. It is metallurgical engineering. That means how we heat a metal, how we cool a metal. The behavior is not same. So if you heat a metal, it will expand. If you cool the metal, it will then contract. But they will not follow the same path. So that is called a hysteresis loop. So what is the behavioral loop and how we can convert that equation to our use? Just like in agriculture, we soak a wheat seed or any rice seed, so it will swell. So if you dry it, then it will be having a different changes in their morphology. So if we can capture that equation and tell, then we can also screen out the quality of the seeds. So this is a different field, but we are applying to our field, like the genetic algorithm. It is the chromosome level and their genesis and other things. That also we are using. And Mars, it is not the planet Mars. It is multivariate adaptive regression splines. So that if we are having the regression equations, we are going for a single equation. But if in the time series analysis, there will be a lot of nodes, lot of changes in the periodicity, then the single equation will give us a very poor R square. So we have to go for splining that. Then for different functions will be for different nodes. And then we are having wavelet analysis, support vector machines, and then Markovian decision problems. Then we know that as also presented in front by our Honorable DG in the inaugural session, data is very important, and the quality of data is also plays a vital role, because if you are having a poor quality data and if you use that in artificial intelligence, like it will be GIGO. GIGO means garbage in, garbage out. So we have to ensure that we are collecting good quality data, and anything coming out of human behavior is called data. I am standing here, I am on a certain elevation, you are sitting at a certain elevation, we are generating data. I am also interacting with so many participants, so I am generating data. So how that data will be used? So this data plays a vital role in artificial intelligence. Now these are the different fields in natural resource management, in agriculture water management, in crop modeling, and also in irrigation scheduling. This tool is being applied. And the basic limitation of AN is that the advantages are there. It can adapt to any situation. And for while modeling, we don't require many input parameters, just like a process-based model requires. We require limited parameters. But the basic limitation is that it is very much location specific. Suppose you have developed for the IRI campus, we cannot apply that to somewhere in Tamil Nadu or Odisha, or we cannot apply that. But we develop the protocol. That protocol can be simulated to other regions. And then largely complex in the network structure, because we don't understand how a neural network works. This is the complexity is there. And now, the work I will be presenting, we have worked on 5 aspects, basically clubbed into 4 categories. One is hydrology. We have applied the artificial intelligence in surface runoff estimation and sediment load prediction. And also we had worked on the land reclamation. We have applied the ANN for estimation of the water quality, the drainage water quality on a subsurface drainage system. And then evapotranspiration we have estimates, and irrigation scheduling also we have done, and modeling crop yield. Now also we are working on something which I will presenting toward the last of my presentation, that this is the publication first we started working in 2004 on estimation of the surface, the sediment yield from the surface runoff. And this is the publication we are having, and I'll tell you brief in 2-3 slides. This is the study area of the Bona watershed in the Damodar Valley Corporation, Jharkhand. The area is 750 hectare, and we developed, our basic objective was to estimate the surface runoff and sediment yield from this watershed of 750 hectare. And we developed a system architecture of the ANN having the input node and hidden layers and output layers. And what is the thing? Because you know that these things are very much black box modeling, because we only get the output data, try to link with y is equal function of x to regression equation, but we don't know what is happening inside. This is a lumped parameter model. So in that case, how we can make a black box to a gray box? We tried in this approach. That means we tried to use some system parameters like the natural drainage network. How many number of drainage channels are there? And that number of drainage channels we try to include in the hidden layers, not single hidden layer. Suppose there are 8 drainage channels, we make that 8, and we could able to see that the accuracy becomes better. So what the results we got? We compared with the regression. The regression was not good. It could able to give only 0.76. Then we tried simple ANN. That is the radial basis functions, GRNN, and this is a feed forward back propagation learning mechanism using sigmoid transfer function, right? Then we use a geomorphology based. That means we use some system parameters. That means we migrated from a black box concept to a gray box concept by including some of the system parameters to that. And there we got the highest R square. So in another study, this was published in Correspondence, that area was in India, and this work is in the Canada. This was the Saint Esprit watershed in Quebec province of Canada during my postdoc at McGill University. I tried to do that. So here I will tell in brief that this is the study watershed in Quebec province in Canada, and we applied the same protocol. And we compared the different rainfall. There we presented the sediment yield, but here we predicted the surface runoff. And we could able to see that with the ANN, with the hidden layers, input layers, and output layers, we could able to get a better result with ANN. But one thing I want to mention that if we remove the hidden layer in the ANN, it is equivalent to a regression model. If we remove the hidden layer in the ANN, it is becoming a regression equation. And then another publication we did with our group at IRI on the land reclamation. So this is the Edakundur village in Krishna district in Andhra Pradesh. The problem was having lot of drainage, water stagnation, waterlogging issues. Then we used the subsurface drainage system. And there, after the reclamation of the land, this is the standing crop in the field. And then this is the concept we used, and we compared with a very good process-based model, salt mode, developed by Wageningen State University. And we see, okay, I want to mention that the ANN is a black box model, and we cannot always tell that ANN is better than process-based model. Process-based models are very good, but the only thing is that it requires data, and data collection, you know, is a very costly, very cumbersome, very time-consuming affair, but there is no substitute of data. Always data collection is good, but we cannot always go on collecting data because due to 3 reasons, time-consuming, very costly, and very cumbersome activity. So in that case, we used a model. So here we use the ANN model, and we could able to see that the results we could, these are the, in salt mode model, there are 20 parameters, but we do the sensitivity analysis, and we could able to use only 5 parameters. That means the artificial intelligence is not data intensive when applied to AWM. Maybe in other fields like medical, I don't know, I cannot say that. But in agriculture water management fields, we are using minimal data sets to develop the, and we could able to see that different type of back propagation neural network, then the general regression neural network, radial basis functions, J-Bessel functions we use. And what we saw, we could able to see that for the 35-meter drain spacing, it was very good, with model efficiency very good. With 50-meter drain spacing, the drainage effluent quality of predictor is very good. And then from the effluent salinity, we compared with the salt mode model. You can see this is salt mode, this is ANN. Sometimes this is the observed data. So sometimes the ANN model also predicted better than the process-based model. So we don't know how it happened. It is very conspicuous, but it happened. And then, but the problem is the ANN could not predict the root zone soil salinity. Because it is a very conspicuous process, you know that the Rickard's equation tells about if a drop of water is falling over the ground, how it passes through the root zone. So the Rickard's equation, that means AN could not able to predict the root zone salinity for 4. And another publication we did on the crop, on the wheat crop evapotranspiration. So this work is also very simple work, but very useful, because last 3 days we are having a good workshop on evapotranspiration estimation by one of the pioneer in the field, Professor Allen, and they are having very complicated procedures, all these things. So we tried to minimize the data and see, can we predict the evapotranspiration using ANN? So we use the MATLAB module for do that, and also Neural Works Professional. And this is the system architecture. And with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters only, we could able to get the actuality. Because actuality how we get? We get the referencity, then multiply with the crop coefficient, then we get the actuality. But directly, this ANN could able to give the actuality. And it is not, we compare to the lysimeter, because lysimeters are the equipments which that can give the accuracy. So you could see that, yes, it worked. And also, these are the daily data I am presenting. And another thing, another activity we did, can we simulate the crop growth and crop yield using ANN? Because for crop growth and yield, we are having 3 growth engines. There is water-driven approach, radiation-driven approach, carbon-driven approach. We are having very good models like AquaCrop, DSAT, InfoCrop. So many models are there. And they require input parameter 130 parameters. AquaCrop is the model developed by FAO recently, which require only 40 input parameters. So can ANN do with only 1 input parameter? We are only giving the plant height and other things, leaf area index, and then we are getting these are the plant height, leaf area index, and these are the input parameters we are giving, and we could able to get with very poor R-square. We compared to it FAO AquaCrop. This is a process model, fine. But still the research work is going on, how we can enhance the accuracy of prediction in ANN for the crop model. And another thing also we did for in the greenhouse impact, we use a fuzzy neuro. Actually, the limitations of ANN can be circumvented or can be addressed by a fuzzifier. So this is the UNFIS, adaptive neuro fuzzy inference system used for the greenhouse seedling, and we do the irrigation seedling. Because irrigation seedling, do 2 questions: when to apply, how much to apply. One more question is added nowadays: what quality of water to apply. But everybody knows irrigation seedling is when to apply, how much to apply. But now, what quality of water to apply is also playing important. So these also. Now I come to my last slide. What are the future prospects? Nowadays, we can automate irrigation seedling. We have developed so many software, so many researchers are working around the globe. Why not we can develop a AI software and embed them in the microcontroller of a sensor, so that automatically you can do that? Because one of my students is also working in that field. We have developed an integrated sensor. We are developing the software. We will be embedding that in the microcontroller and see what is working. And then imaging techniques are very important. The variable rate irrigation. If you have because as mentioned by previous presenters, the imaging technology is more than the natural system. So if we can see a plot, it is moist from the imaging technique, and apply that to the variable rate irrigation, then we can tell in the precision farming, okay, we can shift our broom in such a manner so that it can only irrigate where the field is dry. So that type of imaging. And also geotagging can be done in AI in a digital elevation model, so that okay, I am in Odisha, that portion, that geotagging can tell me that the farmer can take this crop there, this will be the water productivity, and how much irrigation will be doing that. So that type of geotagging can be done, and we have the mobile applications now. This will be very easy for us to know that okay, this is the real-time decision we can make with that. And also crop yield and water productivity can be done. And again, I told you that. And one more thing, in the weather prediction, because we are having different radiative carbon pathways, different IPC scenarios to predict the weather, but they are not sometimes so much accuracy problem are coming. So we are going generating some weather generators like ClimeGen and L-Thea from Cranfield University, USA. So if we can include that mapping using the artificial intelligence, maybe ANN or genetic algorithm, then the climate generation for the future will be more accurate. If we can more accurately generate the climate, then we can predict the impact of the climate change on water management more accurately. So these things can be linked. So these are my conclusions, and thank you very much for nice hearing. If you have any question, I'll be happy to answer.
Keep the conclusion for a moment at questions.
Okay, thank you, sir.
The last presentation is from Mr. Unnikrishnan.
Good morning. I'm having a little bit of a problem with my laptop because I'm using my own. So give me a minute, sir. But I'm sort of the only outsider here compared to all of you. So give me a little bit of leniency on this. Good morning. Thank you for this opportunity. Thank you, ICAR and respected members on the dais and members in the audience. What I wanted to do was to give you a larger perspective, which we are seeing from the industry on what's happening in AI across multiple spectrum of application areas, and also give you a direction which we are seeing on how this is assimilating into change into change across the paradigm of operations which we are seeing now in these industries. So let me quickly start this. Give me a second. Okay. So, like I was saying, right, across every industry, whether you take it from oil and gas all the way up to automotive, we are seeing that AI is revolutionizing that industry. From its micro level workflow process to the entire business model that industry is working on. So for oil and gas, for example, the process of finding the oil to the work involved in every section of it, it's changing. You look at cities, AI cities is a complete AI problem. From analyzing the CCTV-based camera to identify that person, his intent, to what he is carrying, to driving the full sensor-based city to work in an automated manner is a full-fledged AI problem. Same thing true for retail. Now, as individuals here in this country, each of you, if you have a smartphone here, believe me, you are an advanced user of AI. You might not know it, but the entire browsing which you are doing currently is driven by AI algorithms. They are pretty much not just serving you what you want to see next, but also driving your behavior on that site. It's non-trivial, the level of that change which they can do. And the capacity for them from an analysis perspective, right? Predictive modeling, I heard a few of the speakers speak to me before there, has moved from that historic analysis, which is what you do with data, till now with big data. You basically did the history analysis and looked at what can be. They shifted from that into predictive, real time, and then into future modeling. This is substantial change. And it also changes the underlying approach which is taken, obviously, with the new approach to AI. And this is being evident across every industry which you're seeing. Healthcare, it is changing our lives and is going to change it dramatically in the immediate term. One of the most advanced users of AI today is healthcare. And think about the impact. It reduces the doctor error to a level which is unbelievable. It augments the doctor's capacity. It reduces the workflow, the entire process of a medical care institution, from a trauma care where the patient comes, where the doctor is not available to do immediate prioritization of that thing because he just cannot check the MRI in time or is not available. The AI will do it now. In fact, the AI is more or less crossing over the doctor's capability in many fields, primarily because in many areas they are driven on an intuition basis. So if not anything, in the immediate term, it's an augmentation for the doctor and also something to support him for his routine work which he's going to do. Healthcare is unbelievably advanced. Same thing for biopharma. Drug discovery, which has been a process, it's a multi-billion-dollar investment to discover a molecule and then take it into a drug, right? This is being shifted by some of the new age companies from something like 3 years, 4 year cycle into 6 weeks, 7 week cycle. We have a customer who has got a new molecule discovered in 7 weeks. We have industry across board taking this up, from predictive maintenance, which is driving almost 40+% improvement in returns, right? Predictive is costly. The preventive maintenance is cheaper than doing it when the actual this thing happens. So if you can predictively decide that this is going to be problematic, it completely changes the value cycle for that maintenance operation. At least 40% saving in returns. Same thing for financial, from every type of quantum algorithms to this thing. Next is automotive. By the way, automotive might look historic for you from your perspective, but automotive has two perspectives to us. One is, at this point of time, an autonomous vehicle is the most complex scientific problem that the humankind has ever addressed. It is that complex to get a fully autonomous vehicle on the road. Second is, it will also change the entire paradigm of machines which we are seeing. everything will become autonomous. So with this large perspective that AI is basically moving across, before I shift into sort of pointing out 2-3 things which I wanted to cover over this thing, I wanted to bring this perspective to you, that why is this so critically important? So you take any business or research problem, right? It's basically at macro level breakable into these 4 components of input, whether it's in data which is given from text, image, video, or audio. And then you're basically asking from that data this question whether this particular item is present in it or not. And that is a detection problem. So if you do that in a data set of cells to identify whether it's cancer, that is basically cancer detection. AI can do that faster, better, error-free than human beings any day currently, right? And that makes cancer detection magical, automatic. Because once the neural network is trained to do this, it just gets that job done with the new data which is being given to it. Your next attempt to it, once you've done this, then is to identify the type, then you look at segmenting it, then you look at from this data, now to look at a prediction. And in the case of cancer, after you identified the size and shape of the tumor, it will be what is the mortality of this particular person, and then you move into a recommendation mode. AI does each of the step magically, automagically. It straight leads you into insight. And that's the magic which industry is looking at. And that's why research also is applying it across these domains. Now, when you combine this together, each of the steps together, you work a full-fledged function. And in most of those isolated functions, intelligence does not need consciousness. You segregate that too, you're basically understanding that you can shift human decisions pretty much anywhere where there is routineness to it. So, 2-3 additional things on this point. So this is broadly, I'm sorry about this. So 2-3 things which I wanted to point out here, right? And this is a little bit not so easy to understand. So deep learning is the new applied AI technology. It is not the traditional machine learning applied, what you did, I did, most of you are doing currently. Now we always obviously wanted to augment our limited capabilities across our muscular capabilities to our optics capabilities and obviously to our brain. So we made this attempt not just now, long time back itself. 50 plus years of structured work on that. And at a macro level, 2 approaches, right? One was an expert-driven speaker before me, sort of put this in right perspective. The expert level, and the second one, but which is now being worked on and is the implemented one, is a data-driven approach. So it went through the steps, and the expert systems was what was delivered to us in that cycle. And expert systems is basically an expert looking at a problem, breaking it down, extracting the features out of it, patching an algorithm together, and creating an expert system. The dependency here is the expert, his time and his domain competency on the topic and also on patching together this algorithm. The data-driven approach is how you and me learn when we were kids. You take the kid out into the garden, you show them a car, the kid says something wrong, you show another car, kid starts probably another wrong 5-6 times, kid starts taking the car correctly, and from there the progression is unbelievable. And he'll start associating that to green car, blue car, etc. 2 things, you did not break it down for the kid, saying the tire is this much distance, there are 2 headlights, this is how it is a car. You showed, kid learned. Learning from experiences. That's the second approach. Now the confusion all of us had, including the great minds which had, was this approach was never successful till now. And the reason it was not successful was we didn't have a compute which was as powerful as a brain, and second was we did not have data to train that neural network. At that point of time, all of us were in the majority. We looked at machine learning. We did that, and the deep learning people were the lunatic fringe. So the same ANN which you showed earlier, same data approach, if you did earlier with the same limited data set, your ML approach would give you a better result, and your deep neural network would give you a pretty bad result. If the data set improves and becomes higher, and if the compute is there available for it to now process that, you start seeing wonders. And that's what happened in 2011, 2012 timeframe. It started crossing over the ML results, and then it started crossing over human performance, and then the world started realizing the change. And that's when they shifted from the lunatic fringe to lunatic core, right? And that's still happening. So you will find the fundamentalists still working and doing. Not that machine learning is not great or anything, but it's a differentiated technique, and you can still combine, right? So this is one. So when accuracy matters, deep learning happens. There is another value to this. So if you look at this curve now, you find that every traditional ML technique is sort of being averaged and represented in the white line. And this is the DL equivalent, deep learning equivalent against that. What you find here is two things. One is that it is reaching the result faster. The accuracy is far higher. It is crossing over human levels. Now, accuracy with an SVM, for example, is in the 83% currently. Absolutely great. Deep learning shifts that into 97%. Probably you will assume that it's just 5 to 7% improvement, but that is strategic. At 5 to 7%, 97%, you are in a position to take a strategic decision. Shoot to kill. Decide this is a plant or a weed, right? And that's why this makes a difference. The other most important thing is, this is robust. Why robust? What I'm meaning is that your neural network trained to recognize a particular solution or solve something can be retrained with data, the new data, with limited effort, which is not what is true in the ML approach, traditional ML approach, because you need to now fragment that again with that domain, change the algorithm and redo it. Here you are basically just taking new data and retraining it. So that's the other thing. And second is, with every new data which is given to it, after it's been trained and reached this new levels of efficiency out here, with every new data, it is further improving itself. For business and for research, this also foundationally changes to another thing. That gives them a single data-centric approach across their enterprise for operations. Now, fundamentally, if you think about it, it also changes everything for us as far as computing is concerned. And it's very, very easy to make this mistake because we are living in this world. What do we do now? We look at a problem, write a software, company packages it and gives it to you. Not happening here. In deep neural network, you and me are not extracting the features. It is a neural network which is extracting the features. Nobody is writing software here. It's a neural network which is writing the software. You are basically taking a neural network and training it with data. The operating environment, TensorFlows, cafes, Theanos of the world are basically just frameworks to operate that neural network and the propagation of the data through that neural network, not the software to solve that AI problem, which essentially shifts the entire computing paradigm into two processes. Training the neural network with your data. Once you train that neural network, got the level of accuracy and efficiency in the performance which you want for that function, you have a trained neural network, you shrink it and put it in deployment at the front end which you want. So assume that you've trained a neural network with cat data to recognize cats, right? And a CNN network to recognize cats. And then it's trained, you have this trained network, you're shrinking it now and putting it behind a camera. Now the camera takes the input in that room, sees a cat, it will say this is a cat. You are no more taking that input, analyzing it using a software and giving that output. Complete paradigm shift into process of training and then using that to get your work done, which is inferencing. No more software. It also changes how you will work with everything which you are seeing. You're no more going to have an Excel where you buy the Excel, use that Excel for putting your data in, format it, structure it, apply formula to it, look at the result, and then come to a conclusion. No. Your new one would be where you basically feed the data to that Excel service and then ask it questions which you want, and it gives you the answers. It is paradigm shifting change, right? No more like what we are doing. This is why it is so critical. Now, I just needed 2 minutes to establish my locus out here, right? My company, NVIDIA, basically started a journey with graphics. And the foundation for that was very simple. We understood the semiconductor microprocessor which you had, which is a standard Van Neumann computer which you have, which is a compute and a software, a storage subsystem attached to it, was suboptimal because the compute was not optimized for parallel operations. Obviously, parallel is more powerful. We built a streaming multiprocessor semiconductor baseline. And the biggest, most complex problem at that point of time was graphics, highly parallel. And we established ourselves in graphics. And if you're looking at graphics today, we are pretty much the de facto standard out there for any graphics application. And we built an industry out of it. The founders immediately understood, same thing, obviously they are originally still understood, applies for high performance technical computing. And then they built the bottoms to up, tops to up approach to it to shift this thing into supporting everything in high performance computing. High performance computing which you are having today is basically after from the vectors based compute is the distributed this thing with the daisy chain approach of a Beowulf cluster, and then you apply onto it. But semiconductor industry was supportive of that because it delivered the Moore's law and gave you double the performance every year. So you and me consumed that and kept doing that. Serial approach, non-optimal. Ours was a parallel approach. The same compute, instead of having few cores, ours had thousands of cores which can work together. But the problem was it needed you to parallelize your codes to use it, which you would never do because it's extra effort on your side, and it did not also fall into your domain competency. You wanted to solve your problem, right? Your agriculture or bioinformatics or whatever. It took us some time to change those codes and show them the difference of it. And today we are pretty much the de facto on HPC also. And it's very simple. The reason is, if you want to build a petaflop of computing, which is what our NSM is doing, it is pretty much this room with the standard approach. For us, on our systems, the petaflop is this much of a system. Now just transport that into economics on cost, on power, on AC, and that's why we have become the default. What happened with deep learning was, by serendipitous discovery, when they tried this approach in this competition on ImageNet, they tried running this on standard compute, and one group of people in Stanford did not have the money to run it on cloud for thousands of computers, trained neural network. They tried this on GPUs, our systems, and they could do this on 16 GPUs, this much, just this much, with a UPS, instead of 1,000 computers, this much, and 5 million versus just $100,000. That made the compute underneath this required this thing practical. The results were 6x better. Deep learning happened. With deep learning happening, and it was a basic CNN network at that point of time, what other thing which is happening is, now you as domain experts do not really need to solve the neural network problem. Every day they are discovering a neural network for a particular area of problem. It's a Cambodian explosion out there. Everyday neural networks are happening. You just have to pick the right one for you, apply it with the data, train it, solve your problem, right? So it's applied. So baseline, we became the de facto compute for AI, and we focused ourselves into 3-4 vectors, which is one is healthcare, second is autonomous robots, embedded, etc. And that's where we are currently. And then we realized another problem, which is critical for you. So this is what has been delivering for us, right? The doubling of the performance, which enables you to get the double the power because we can pack double the number of silicon in that same real estate. That is tapering off because physics is hitting it, right? Which is happening at a particular point of time when the compute demand which you have as an industry, as an individual, as a scientist, is exponentially raising. Whereas from our approach, we continue on this journey, we are still able to deliver to you 500x plus in the last 5 years, and we can continue for this next 10 years, which is why we are pretty much the compute underlying for everything which you are seeing in any of these domain areas. Today we have a full-fledged, I'm explaining this to you because most of you will start using this, and I wanted to give the perspective and the value proposition in multiple domains of it, right? And I heard somebody say here, please learn TensorFlow, right? And that's why I'm making this a little bit more detailed. So we went then and completely transformed ourselves into an AI company end to end. For the back end, for building your supercomputing systems, for training the neural network, and in the front end, for putting it into the edge devices, whether an autonomous car or your drone which you're seeing, or you're behind your microscope to look at the new image analysis. Full-fledged AI thing. But there is a massive thing, two things which we did, right? So the software stack underneath this, like I said, is the operating frameworks, 30 plus out of them, TensorFlows of the world, cafes of the world, being built by open source community. They are but developing on that on their own pace and their own improvements which they're building. It's an open source environment. Each of those softwares need to now massively use the massive compute which is needed to now look at the deep neural network processing on it. And each of them moves separately. Each of them needs an underlying stack which is different from the other. So if you buy an infrastructure, want to run it on TensorFlow, and another person is attempting to do, let's say, a GAN network, and it's using Caffe, then he needs to completely change the underlying stack to support that. Your IT will go mad, you will go mad because of the infrastructure. What we went and did was two things. One, we optimize and continuing to optimize every one of those softwares when the open source moves that software by putting our engineers on there. Then we made a container equivalent to your basket, equivalent of that in operating environment in compute, and is putting every underlying stack in that container. So, and then giving it to you free of cost. So all you need to do is that I want TensorFlow, and then go to our website under this account, click it, you have the most optimized TensorFlow available for you to run on any GPU environment. Solves all your problem. And because it's containerized, your colleague can run Caffe simultaneously. And that solved the world's problem on this. And we're continuing to do that. And that's why you're seeing people getting this into production at the level of pace which we are seeing today. And please comprehend this very clearly, because the problems they are attempting is unbelievable. Like I said, autonomous is the most complex problem which you have attempted as a human being ever, right? So I'll not go into detail. Anybody who's interested in technicalities of this can speak to me. I just wanted to cover 2, 3, 4 more points, right? So we are in the era of AI. But this is a substantially different era than what we have ever seen now, right? And there are 4, 5 points into this. In this era, these are the 3 things which matters. Data, the new algorithms which the scientists will develop, and the underlying compute to make use of that. Essentially, but software writes software, right? So it's no more the other way around. The other factor which you have to think as people who are going to drive the agricultural revolution for us in this country is that the impact of this is across every sphere of our life. It essentially said that if you take more than 1 second to do anything, to think and close anything, AI will do it better. That's the level of the impact on AI. It'll change every aspect of your life. Second, third probably is this aspect of velocity. Now, every technology change over our life has gone through multiple time frames to make that change happen, right? In the recent times, PCs took 15 years. The mobile, to get into our pocket, into our mate's pocket, and everybody's took just 7 years. We think AI will do this in 2.5 years' time. 2.5 years is not enough for you to sleep and come out of it, right? For industries to change. But the differential out here is the difference between the haves and have-nots are going to be substantially different. India could afford to do a 2.5 year gap on technology adoption and still balance. We cannot do this on AI because we'll shift this ourselves into a consumer rather than a provider of this. So this velocity is unbelievable. And the factor on this velocity is it will also not be ever this slow again in our history. The space of change, right? The other part to it is it'll make everything pretty much at some level of autonomous, fully or some level of autonomous, to everything which you can see, your tractor, to your weeder, to to your harvester, to your full combine, right? Other thing is a bunch of complementary technologies which is happening in genetics, in bioinformatics. All of them are at a maturing phase, in robotics, in nanotechnology, or at a mature, and AI is accelerating that further, right? Now, but the most foundational change is going to be the business model changes. And it's very, very difficult to understand this because you cannot predict how it will change. And it's also easy to not look at it, particularly for people who are in the business. But business model change is paradigm shifting. You think about a 200-odd industry like your taxi cab industry, which has just got completely paradigm shifted by Uber, who does not own a single car. AI will change this like nobody's business, right? Just think about it. It's leading you straight to insight on many areas, which means it will change business models for all of this. AI is revolutionizing agriculture, every aspect of it, and AI is the most advanced use in precision agriculture currently. Across our user base, we are seeing this happen, from harvesting to all the way from field preparation to planting, seeding, crop care, harvesting. It's making it happen. And it was always happening, right? We were, in the last 4 or 5 years, the outlook over the technology industry in precision agriculture was to make bigger machines, right? But that's shifting with the new approach to AI. It's now making new things possible, right? Till now, the technologies couldn't recognize texture, shape and size and quality of that particular plant. That's possible today, right? Just because of imaging improvement, right? So new modes of farming is possible. It's also shifting our capacity to do everything from a data to decision into the better way, right? From it being doing it in a batch into a real-time mode, from being broadcasting it into driving it to a personal level, and either at a particular plant or at a human being level, and from making it specific to a particular instance of a decision. So you're basically now able to do decisions real time, right? And the equipment is also it's changing, it's making it smarter and autonomous, right? So essentially it is completely shifting across all vectors to make right input, right amount, right time, right place happen for agriculture, right? So fertilizer, soil at plant level, right amount, changes the paradigm. You are the domain experts. I needn't tell you how it changes, right? It affects our environment, affects the input costing, it improves the output, and you have already made interventions. ICAR has done this project with Microsoft. You've heard about Plantix. So it's happening, right? And it's happening at a pace which is unbelievable. So I have just 2 more points to make, and I'm done. So for India, what we're telling the government and everybody is these 2 things. You have no option but to apply it across your industries. It's a do or die situation. And second is, we have the opportunity to be the global AI talent provider for the world. Now you have to understand one simple baseline logic here. This is an applied technology. It does not have a foundation in engineering or anything. It basically is mathematics, science, philosophy, statistics, etc. Agriculture student can equally study it, apply it, right? We have full-fledged course material available for you. Just start an elective. We will support you whatever way we can, free of cost. Get it for your degree courses, adopt it. Please make this happen. Right? And AICT is already changing it. Ministry is making it. I'm hoping you have seen the AI policy document which has come out of Niti Aayog, at least the discussion paper, and hopefully this will translate into some actionables. It is obvious that we have disruptive possibilities with AI. But the problem with India is we are many Indias, and this is unbelievably complex and differentiated compared to the rest of the world, right? For us, reality is still this. I picked up this image from the net, but this is still the reality, which means our capacity is there, but we need to think out of the box. I am no expert on this, but there is few things which I think obviously make sense. First is that data is the core cornerstone. So we need to ensure that we are working towards collecting data at every level, preparing it, making it ready. But the mistake which we typically do is we collect the data, keep it to ourselves. Doesn't help. We need to make it open, available, usable to everybody. We need a centralized data factory. The neural networks are open source, available, created by everybody, combining them, applying it, training neural networks with this data and making it semi-ready for an applied environment is going to happen. We need that also to be either taken up by a central resource applicable for this domain or created into a PPP type of environment. The other two components are primarily technology and equipments, robots, autonomous agribots. Professor visited the University of Sydney, unbelievable work they're doing. And yes, all of them are applicable here also. But we need a differentiated way of getting this out here because of the cost and the small fields which we have. And finally, we need to, like I said, do the skilling at the agriculture university level and also reskilling at the farm field level. Right? And we need a differentiated approach in every one of this. So data, like I said, needs to be common source. And that's something which an institution at the government level probably is in a better position to do it. Make it open, accessible, available to everybody, and owned by us, right? And protected at whatever levels it needs to be protected at. Algorithms could be a PPP and made available, right? And we need this to happen. Technology and equipments could be a cooperative, an Uber of it. And I think a startup is already on that direction, right? And same thing for skilling and reskilling. With this, you can disrupt Indian agriculture. I'm pretty sure about it. I'm an outsider, so pardon my ignorance and what I don't know. Thank you very much. I really appreciate it. I leave it to you to finally have 2 minutes of this, which might sort of give you a glimpse of something happening in the industry.
So, thank you, Mr. Yuning. You can join the dais here. Yeah.
If you can give 2
Okay.
minutes, just 2 minutes.
Where did you stay then? You are outside.
Sorry, I think this. I'm just having a problem. I'll play this for you. Please, sir, continue.
So, I request all the presenters to come at the dais. So, we had the wonderful presentations made by all the 4 speakers from the ICAR and also from the others, and especially by Mr. Unnikrishnan giving the whole gamut of where we can approach into and what is happening in other industries. So we can have questions, 15-20 minutes.
Good morning, everybody. I am Mesan Islam from ICAR. My question is for Mr. Unnikrishnan. You talked about the traditional machine learning and deep learning again. It is, you told that it is, it gives you, the traditional machine learning gives you 80% of accuracy. And for the deep learning, it gives you 90% of accuracy. For normally, traditional machine learning again, we train the machine for around 20 to 25 years of data. This is again a cumbersome task of acquiring that and training the machine. So, how much you think, how much additions needs to be done in form of data? And the next thing is how you want the machine to be prepared in terms of data, in terms of process, and in terms of mechanism for this deep learning. And this is just a theoretical perspective, or have you, this 90% accuracy has been achieved in any of these processes, what you have taken up?
Press and keep, okay. So the level of data needed in a particular area is dependent on that particular domain in the area. So there is no generic rule to it. It is probably going to be higher than what you typically do for machine learning, right? The preparation of that is also dependent on the particular problem which you are trying to solve. And the accuracy reached in a particular domain is also different. So there is no baseline across domains, it's 90%. What I did refer to was on image processing, right? On hyperspectral image processing, which is what you referred to in GIS presentation here in the first presentation did. There, your current most advanced machine learning technique is SVM. And SVM's best results are in the region of 87% odd. And we're getting around 97+% in that in deep learning. So it's domain to domain, but we are seeing at an average the AI approach with deep learning far better on pretty much all domains. Image processing, 100%, definitely. NLP, definitely. Audio translation, definitely.
So suppose vector machine, you say that it is 87% accuracy is there. But what algorithm for deep learning? Can you elaborate, and have we ever achieved in any of these? Yeah, because we are
no, so all of the things which you're seeing is the actions which are happening today is because of that, right? So you are having today, for example, in MRI, the AI is recognizing the MRI images far better than doctors. Diabetic retinopathy, it's doing the same thing. So you name the area, it's happening today. The new applied approach to MRI recognition is on deep learning. I can show you some data and results.
Sangwan. First, I congratulate the organizers, because last 4 or 5 months I was struggling with the higher-ups to have such a conference. I am very, very grateful them, at least they have started and made a beginning. You are talking about the prospects. Nobody is doubting the prospects. Even sky is not limit for artificial intelligence. From the farmer's perspective, I just want to ask the last speaker. You said there is a huge scope in artificial intelligence in agriculture. I'm a farmer. I want a small tortoise type machine in my field which can walk through the furrows and remove all the weeds and give fertilizer to each plant and tell me about the insect pest, tell me about the moisture condition, and do lots of other things. Do you have on the ground? If you have it, please tell me yes. Otherwise, leave my question here as it is.
Sure, sir. I do not make any of this machine, so I'm a technology provider. But just to answer your question, those are the realities which will happen in the immediate term. Currently, there is available technologies, and I can show you immediately, which can recognize plant and weed. 10%.
Any camera will recognize anything if you change the system. That is all things available. Artificial intelligence today also it cannot work if we don't have already available data.
Without data, it will never work, right?
You have to work only something existing.
Yeah, so I'm telling the same thing to you, right? So there's a company called Blue River, which is responsible for 90+% of the lettuce production in US improvement. They do exactly what you asked. Currently with their technology, you just can go to YouTube and watch their video. You Professor talked about University of Sydney, right? Yeah. So.
So we have seen that machine, what you are saying, Ladybird, and the University of Sydney, and we have seen practically the machine. And the same thing, it moves to the ridges, and wherever the weeds are there.
In India?
No, Australia.
I'm talking about India. I'm from India.
Yeah. But you can purchase the machine. You can purchase the
Then what we are.
Okay. Please listen. Your question, please.
Hi, I am Anil Rai. I'm in bioinformatics in ISRI. I saw the presentations. So few presentations I saw R square is quite high. R square means about 90, 95, 97%. And it's very good actually. But just for clarification, for my clarification, R square is not actually a measure of accuracy basically. And actually we should go for the error estimation through cross-validation technique, because R square 98% is quite misleading for this kind of work, especially for ANN. That is my experience, and as rightly pointed out, AI I think is not always very good for all the data sets, because we have worked lot of work we have done on machine learning and AI. And for some of the data set, AI is very, very good. But some of the data set, SVM is also very, very good. SVM performance is found to be better, especially when the data size is very small. So whether I am correct or not, that's what I would like.
Sir, you are right that looking into the error statistics, it is not that we have estimated only R square. We have the degree of agreement, model efficiency, and root mean square errors are also there. But you're right that sometimes it so happens that due to the inherent data structure, we also randomize. That means the placement of the data in one record, other record, there will be compute biasness. So by default, the computer will learn something. So what you do, you randomize the data many times, and sometimes the R square also varies from 0.7 to 0.9. So we generally do that. It's really right.
My point is the R square is only good
it's highly biasing.
Linear models.
Yeah.
And ANN and this kind of models, they are not linear and they are not statistical basically.
Right, sir.
By nature, they are not statistical.
Sir, I supplement with Dr. Anil Rai. See, for example, the correlation and agreement. Correlation and agreement. One set, three numbers I will tell. X 1, 2, 3, Y 4, 5, 6. Good correlation, but no agreement. There is no agreement. So this R squared is not an accuracy measure, it's still a measure.
So actually the MRI it is working, might be working more, but agriculture is a different situation. The data set is open field. Okay. MRI also, patient will not see the MRI and take the decision. It's the doctor who will see the MRI. The system will help the doctor to improve the efficiency. Similarly, you have to build the systems to improve the efficiency of extension scientists, efficiency of the breeder, efficiency of the meteorologist, whatever it is. We need to start a lot of research projects. It is not just silver bullet what you are saying. It will come after doing a lot of research. So you have to spend about 4-5 years rigorous research, because agriculture is completely different. I am also a computer scientist. It is also agriculture completely different from the medicine also. Here you see the eye, you take 2000 pictures of same position, then machine learning system will work. Crop is not same. You will say photograph anyway, it has contained 20 pests, at least 10 diseases and 5 to nutrition deficiencies. You have to build a system by doing a lot of intensive research for each crop, as well as each stakeholder also. There are different stakeholders. Farmer is not only stakeholder, there are several stakeholders. That is my comment.
So I sort of seems to have given a wrong impression probably to few people that there is a silver bullet that I prescribe. I was only saying that the applied technologies in other domains are equally applicable here, and you need to do the rigor required for that particular domain, right? And that's happening as we are speaking. And because of that rigor, the people who have applied it is getting that advantages and this possibility. So I'm not saying, sir, that
lot of preparation is required, lot of training is required. It's not that working means that that is the whole of broad statement. It is working under certain situations, certain field preparation. Like, but is it possible here? What are the massive amount we require? You would estimate that. Okay, thank you.
Myself Nagarjun Kumar from Treda. So my question is Dr. S.K. Ambasniji. So in the presentation, you told that albedo value is fixed. So I want to know on what technique albedo is fixed in that, and also whether it is standalone application or web-based, so and whether it is validated at the farmer's field. It is my question.
No, I did not say the albedo is fixed. I don't remember that I said like this, because the albedo image has been created based on the estimation, the data which is available in 7 bands of the ETM, that has been integrated, and that has been for the entire visible spectrum. The albedo has been worked out, and albedo versus NDVI, this plot has been created, and there was a pattern which we found, and this pattern has been used because even the visual interpretation, we are not able to see the number of shades. We can, because there are 255 plus 1, so 256 shades are there. So we developed the algorithm to classify those 256 shades and different crops into a class, and that became the class 1 to class 7, where the class 1 is waterlogged area or class 7 is highly salt affected area. So there was nothing like this fixed.
I am Sumant Kumar from ICAR NAM. My question is specifically to Mr. Unnikrishnan. Like when we execute a Python code with Google Collaboratory, Google Drive, it asks a option like whether you wanted to execute this code with CPU or GPU. When you select GPU, after that we can see the configuration of entire GPU. It always comes NVIDIA to be the GPU. Is it? My question to you is, entire Google Cloud is completely built by NVIDIA as far as the GPU is concerned or not? Thank you.
That's true. Pretty much, and Google, Amazon, Microsoft, all of them, the GPU cloud is on NVIDIA.
There is no other as far as except NVIDIA on this?
Multiple players actually, right? See, at the end of the day, it's a compute. So CPU will also work, but the issue of who's most optimally available for you at the right cost and the right performance and the right stack supporting for you. It's a choice after that you make, right?
Empanelment of IT forms you have presented in your presentation. So that product will be with you or with IT firm, sir, and expertise maybe our expertise only, I think, sir. Maybe how you will do this one and commercialization part.
Actually, it's a very innovative kind of approach what we have started. The companies, they will have their own, as NVIDIA has the different kind of expertise. Then we have the different kind of expertise, the technology domain. And then we both come together. And then what is our requirement? And because we cannot be as expert as they are, and they cannot as expert as we are, as far as those domain things are there. So then together, we develop a product as per our requirement. Not per as company requirement, as per our requirement. And if this product is successful, the license is given, and this product is for us, let us say now, or DRR, you will be using for whole life. And this product, when it is sold to the other stakeholders, then whatever royalty is there, we get 8% of this.
8%?
Yes.
And those people, if they want to commercialize?
Yeah, they will only commercialize. They will only commercialize. Yeah, Nasuddin.
I think it's a very good beginning in this sense. The same question I'm telling, but we have, I think, valued ourselves quite. When the product is, see, software and other things are there, but the main thing is domain knowledge.
when we are giving that, developing that project, 8% is pretty low. It should not be more less than the 40%. Right? So that's the value
Hey, Dr.
we seek
Soam.
in ourselves. That's the value we seek in ourselves nowadays. And it has to go above.
Mr. Marwa, this is not the...
No, that's what I'm saying.
Yeah.
I'm not that.
Yeah.
But the effort is very good.
तो सूद
But
ना
I
कपास
want
से
to
जुलाओ में
say that our value is much more.
तो सूद ना कपास जुलाओ में लटकम. So let us have the beginning.
That's what I'm saying.
No,
Good.
no, let us have a beginning. And if we feel that 8% is low, though 8% is very high as far as these people, private people might be knowing, 8% is very, very high in the industry. Even if we feel that 8% is low, you don't do. It is in our.
That's okay. It is good.
Yeah,
Start
it
is
is,
beginning is good.
but it is just a beginning, and the whole exercise we have done, and through tender, our side is here.
There is no need to discuss on this issue.
8% is high.
See, this is your product, keep it 100%.
Yes.
If you stay only 8% or 2%, how you can claim 100%? So let us have some more questions which are more interesting.
Good.
So probably no question now, so I will take 2 minutes, 1 or 10 minutes. It was very interesting session, and also it is presentation made by Mr. Unik, how he is in other sectors. So it was very interesting for me also, and the way it was presented, how our own people have used in the field of agriculture. Some cases has come up, and basically those areas where we are concerned, whether it is soil related issue or even water related issue, Dr. Ambast and his team has done a lot. A beginning has been done, though we are not doing that, is it AI or what? But it was already in practice in many places. Institutes were doing, our own ISRI also, their team has been doing it. So is the NAM, they have come with certain innovative ideas that how we can make it happen. And what we personally feel, going through all these discussions, that when a new technology comes, new innovations comes, people start opposing it. That how it will happen, we are a very poor country, farmer doesn't know, we are also not aware of. But later on we find that when there is a ease of using technology, people accept it and they start adopting it. And we have seen how quickly mobile phones, we also were not very free to use the mobiles earlier, but everybody is having now all those mobiles, and many have got more than one set. And today it was mention of iPhones was made about the use of Sri, and there is one small child in my own house. She is barely 5 years. She pushes that button and calls Choo Choo TV. She doesn't know anything, but Choo Choo TV comes on mobile and starts seeing that one. So definitely there is advantage of AI, and if you look into the drudgery aspect when going and working in the field of agriculture, especially driving a tractor, operating certain machines, very difficult one. People do not want to go, but they have to go because there is no other option. But if something comes of this utility which can be utilized, so the human capital can be used to the better areas where they can contribute their mind and also the labor. But nonetheless, the human factor, as we have been telling, cannot be ruled out. Machine will always work on what we actually administer to the machine. And we hope that ICAR, we have got a lot of area to do, a lot of crops are there, a lot of characters are there, and so many parameters are there, how to deal with. And we have to provide all the information to the domain, only then probably it will be serving the way what we want. Few years back also there was estimation of basmati rice, probably it is going on a regular basis by EPIDA. And using all those remote sensing, even today there is a ground truthing also. People go on sites with GPS and they also find whether what satellite is telling, whether it is correct or not on the ground also. So having both things together, it's the real person going and making a kind of estimation, and also the satellite support. Definitely it's ease, accuracy is there, correctness is there, and timeliness of course, and the cost effectiveness, speed already spoken about. So everything is of the advantage to the society if you can do. If something is predicted early, losses can be actually overcome. And we have seen, especially in the case of weather advisories even today, whatever little bit accuracy we have got, farmers are saving their irrigation water, farmers are saving the pesticide use, which they could spray. They are avoiding that today it's going to rain and if you spray, it will be all futile exercise and whole money will be lost. So there are effective the measures which we are already taking up, and I hope this session lot of information has been generated. And yesterday forenoon session also I was throughout when DG was there and also Mr. Amitabh Kant, and then thereafter also one full session. And so many new things we are also learning, and we'll encourage that this kind of science goes into our agriculture sector. And those initiatives made by our own colleagues in ICAR, I congratulate all of you, and I hope that it will be done on a faster speed. Thank you very much, all those who have made presentations and all of you who were there in the part of this discussion. Thank you very much.
Thank you so much. Before we close the session, we have mementos for the speakers. I request Chairman to please give the mementos. Dr. S.K. Ambast. Chaturvedi ji, please enter. Dr. S.K. Som. Dr. Sarangi. And Shri Unni Krishnan ji. And now I request Director NAM, Dr. Srinivas Rao, to please come on the dais to facilitate the chairman of the session. Thank you so much. Now we can break for the tea for 15 minutes break, and then we'll reassemble by I think 15 minutes is the tea break. And I request the speakers of the next sessions, please upload their presentations so that we can start the session on time.